Thank you.
All right, then let's get started. Great. Uh, you guys can see my slides, right?
Yep.
Okay, cool. Okay, so outline vectorization summary of its advantages. Then we move on to the lab and homework. We talk about vectorized sawtooth as signal waveform, and then finally the Fourier series approximation of the sawtooth signal. Okay, so is anyone here taken a course in basic electrical engineering? Are you guys familiar with sawtooth waveform by any means?
Yes.
Yeah, a
Okay,
little.
great, awesome. And the math behind it, or is it just you know how a sawtooth waveform looks like?
I mean, in what reference do you mean the math?
So, for example, if I ask you, can you tell me what the instantaneous signal at any point in a sawtooth signal would be? Do you know how to get that?
No.
Okay, so hold on, chat box, I believe. Oh, okay, great. Okay, so let's start with vectorization. I believe that you were introduced to the idea of vectorization in the lecture Tuesday. So brief overview. So when we generally define a function in Python, we take in as an input a scalar value in the function. So for example, if we have y is equal to fx, so we might write def function with the inputs x, and that x is generally considered to be a scalar. And if you have to call the function over and over again, what you do is you pass it through a loop and you store the results of the function in an array. And if you have to plot them, you plot the scalar values against the vector of the function values that you get, right? That's what we generally do. What Python allows you to do, and there are other object-oriented programming paradigms out there which allows you to do is a vectorization. So instead of passing the input as a scalar value, what you can do is you can pass x as a vector. So let's say you have a function defined def func x, something like that. And so what you do is you write that as let's say you want to store the output in some array or some vector y. What you basically do is you write y is equal to within square braces f xv. Xv is just a name that we took for looping or iterating through the loop variables. So fx of v for xv and x would give you a bunch of values for y. Okay, and to remind you, you did use vectorization in homework 2 when, if you remember, when you're doing this play map average thing for n and n set, for t and t set. That is what vectorization is. You were looping through, you, or rather you were passing a vector to your function play mab average, and what you were getting as a result was also a vector. Okay, does it make sense?
Yes.
Okay, yeah, and to extend a little bit on that, one of the ways that you could have done that is like define two for loops for t and t set, and inside that another for loop for n and n set. Then you define maybe an empty matrix or empty list of lists f set maybe. So you write f set I of j is equal to a mab average of n comma t comma m and whatever the inputs are. If you I mean, if you have time and you might want to run this experiment, that trying to get values by using for two for loops would take you much longer than if you were to pass them as vectors. Okay, just try it out at your own time if you have, and trust me, you're gonna get a much lower running time if you were to pass it as a vector. Okay. Some of the advantages: performance improvement. Like I said, it enables you to decrease the running time of the algorithm by several magnitudes. So if somebody over here is familiar with theory of computation, so when I say running time, that it doesn't mean the complexity of the algorithm. Okay, are you guys familiar with the complexity of an algorithm and running time and stuff like that?
Yes.
Okay, so when I say running time, it doesn't mean the complexity. The complexity of the algorithm stays the same. So if you're running, for example, for n and n set, for t and t set, and let's say you have n elements in n set and t elements in t set, your complexity would be n times t. Okay, it's straightforward. and if you pass it as a vector as well, so if you write within square braces, play MAB average for n and n set for t and t set, that's still going to be n times t. But what happens is that you're reducing the running time. Okay, you're skipping some steps in between. That's all. Right. So you can leverage the advantages for matplotlib, which you're going to do for this lab. It's for the homework, and NumPy for the record has a method to vectorize. It automatically does that. So for example, if you define a NumPy array, and a classic example is the play map average, right? So what we were doing, we're not doing anything else other than writing two for loops within square braces to pass it as a vector into the play map average function. Okay, so that is all that it's saying. Any questions before I move on? All good? Okay.
Yeah.
Okay, so overview of what you're supposed to be doing in the lab and for the homework. So in the lab, we're going to mimic the square wave example and create a sawtooth waveform. I believe you saw a square wave example in the lecture. So in the lab, you have to create a sawtooth waveform using the similar methods that you learned in the lecture. What do you have to do? Define the function, implement a Fourier series approximation. Equations will be given to you. Plot the function as approximation. The goal is that you have to write a vectorized function and plot it, right? You can't possibly use for loops, like nested for loops to do that. You have to pass it as a vector. That's the deal. For the homework, again, you have to, now for the lab, it's all 2D plots. For the homework, you have to take it a notch higher and deal with 3D plots. Nothing different apart from the fact that now you have to pass in three-dimensional data, or your function is now a multivariable. So where you take two inputs, f, x, and y now, where both x and y are now vectors and not scalars. And what you would get as an output is an array. And you basically plot it using the same method that you saw in the first matplotlib lab. You define a mesh grid and you pass that as an input to the mesh grid and you get an output, okay? Not too hard, trust me. If you can use the first lab material as a reference, I mean, there are like thousands of materials online for plotting 3D plots in Python. So that's not going to be hard. And it's not about matplotlib. This is about vectorization. It's about understanding how you can pass vectors as inputs to a function and stuff using multiple for loops to pass in scalars and get a value for an array. Okay. Somebody is chat. Do we need to mesh grid? Yes, you need to use mesh grid to create a 3D plot. You can use the exact same method that was shown in the first matplotlib, that is week 2 lab. You can use the same way to generate that plot, except the function now changes. It's going to be whatever is given to you. Does it answer your question, John? Cool. Okay, so that's all about lab and homework. So let's move on to the next plot that we have. Okay, vectorized sawtooth and signal waveform. So what are the sawtooth signals? It's a periodic signal where you're given the period, that's capital T, and you have a minimum value for the amplitude and a maximum value for the amplitude. Capital T is a period of the waveform. S min is the minimum value of the amplitude of the signal. And S max is the maximum value of the amplitude of the signal. It's a no-brainer to assume that the period of a signal has to be greater than 0, right? It can be less than 0, otherwise you won't have any signal, right? And it's also obvious that the minimum signal value has to be less than the maximum signal value again. At any point of time within a period T, your signal would begin at the minimum signal value and move all the way up in a sawtooth form to the maximum signal value, and fall off in a perpendicular fashion to the minimum signal value and start over and over again. Okay, let's take a look at an example. This is what a sawtooth waveform would look like. Okay, so we have some certain S minimum, certain S maximum, and this is my signal versus time plot. If you take a look at the time period, it's all T. Okay, so this is one waveform. We start from here, go all the way to S max, and we drop all the way down here. Then we start from S min. Is this what called a triangular wave? No, John, this is not a triangular wave. A triangular wave would look something like, so if I were to invert this, So let's say it would look like this and this, and it would look like a triangle, not a sawtooth. A sawtooth has one of the sides is vertical. Okay, so this is dropping perpendicularly from S max to S min. There's a difference between triangular and sawtooth waveform.
I'm sorry, try to
Yeah.
be picky, but could we try to just put the mic like down?
Sure.
It
Yeah. Yeah.
honestly might, it
I
might sound better. Honestly, I don't know about what the rest of
yeah.
you
Sure.
guys.
Is this better now?
That actually does. That sounds a lot better for me. What about you guys?
Yeah, I think it sounds better.
Yeah, it sounds
Oh,
good.
okay. Yeah. Last
All
time
right.
people can hear me, so I thought I would put the mic close to me. But
Yeah,
okay.
it just sounded like you're eating your mics. Sorry about that. Thank you.
I know. Okay. Thanks for letting me know. Okay, so that's a sawtooth waveform. So basically, again, you start from a minimum value of the signal, go all the way to a maximum value, and then you start over and over again. And if you take a look, the period for all the waveform is t, right? So for this second one, it starts from t, goes all the way to 2t. From here to 2t to 3t. It's always capital T. That's the time period of the signal. Okay. Uh, so if I have to put this in a mathematical waveform, in a mathematical form, I can write this as signal or the instantaneous signal at any point t, small t, is equal to the minimum value plus t over capital T minus the floor of t over capital T times S max minus S min. Now this all looks a little complicated. Take a moment. Can somebody tell me what this part of the equation means? Does this equation look familiar to any known equation that you are familiar with? The, I mean, in any equation of any uh, mathematical form that you're aware of that looks similar to this. Matt says y is equal to tan x. Why do you say tan x, Matt?
Because it's a repeating pattern, and like a tangent of x would go to infinity, but it has it like crosses.
Okay, so you're saying that there's a phase involved over here, right?
Yeah.
Okay. Good guess, but how about something simpler? Okay. So to give you a little bit of hint on that, your phase over here is that your t value, your small t value is always increasing, right? We are starting from 0 and going all the way to whatever the final value of t we have chosen to be. So we don't necessarily have to involve any trigonometric function to get a sense of the phase, right? How about something simpler? If you're in the Euclidean space or the coordinate space, does this look familiar to any equation that you know? Let's say I get rid of this floor function. Okay, let's say I have S min plus t over capital T times S max. Okay, so we don't have this guy and we don't have this guy. Okay, if I get rid of these two guys, does that? Yes, exactly, Timothy. Y is mx plus b. That's an equation of a straight line. Does it make sense? Yes or no?
Yes.
Exactly.
Yes.
It's an equation of a straight line. The only difference is we are taking an intercept, a difference of an intercept. Okay, so t over t is the fraction of time. So let's move on to this slide over here. So I'm pretty sure you guys are familiar with the floor function. So if I take 1.25 and if I take floor of 1.25, that would give me the integer 1. Okay, that is what a floor function does. It gives you the smallest integer closest to a fractional decimal value. Okay, so that's a floor function. Now, what is t over capital T? T is my time instant at any given point of time, and capital T is a period that is being provided to me. Okay, so t over T is a time in units of period. So it's basically the amount of time you're spending. So let's say let's go back to the plot. Okay, so at any given point of time, this is my period, right? And t over t over t, small t over t, is the units of period or units of time elapsed since I started moving away from S min. Does that make sense? So my period, total period is t, right? And small t is, let's say small t is somewhere over here, okay? Somewhere over here. This is my small t value right now. Small t over capital T is the amount of time that I've elapsed within this period. Is that making sense? Yes or no?
Sorry, could you explain that again?
Sure. So let's forget about all these things, okay? Let's suppose you have just one sawtooth with the period t, all right? I'm saying capital T is the value which gives you the time elapsed since you started moving away from the minimum signal value. Let's say capital T is somewhere over here, okay? Let me zoom it in. Somewhere over here. This is my small t value right now, okay? And this total time period for the sawtooth is capital T. So small t over capital T is the fraction of the amount of time elapsed since you started moving away from the minimum signal value. Does that make sense?
Yeah.
Okay. All right. So let's move on. Okay. The floor of t over t is the number of periods that have elapsed by time t, okay? What does that mean? Again. So we understand that small t over capital T is the amount of time elapsed since we started moving away from the minimum signal value. If I could, if I could divide this time period into some equally spaced intervals, if I could divide this time period t into equally spaced intervals, then my small t over capital T value would lie in one of these intervals. Does that make sense? If I could divide my time period capital T into equally spaced intervals, then my fraction small t over capital T would have to lie in one of these equations, one of these intervals, right?
Yeah.
Okay, cool. If that is the case, then the floor of t, let's take an example. Let's say capital T is equal to 2, all right? And let's say t is equal to 1.5, let's say. My small t is 1.5, capital T is 2. Now, and if I divide my time period of t into 4 intervals, that is half, 1, 1.5, and 2, right? These are my 4 intervals that I've divided into. Now my small t value is 1.5, right? If you take the floor of 1.5, you're going to get a 1, which means since you started moving away from the minimum signal value, you have moved past 2 intervals, that is 0 to half, half to 1, and now you are from 1, 1, and 1.5 in that interval. Okay, so what are the number of intervals, or what are the intervals that have elapsed or moved away from since I started? So that is 0 to half and half to 1. Okay, is that making sense? Yes or no?
Yes, it makes sense.
Okay. Right. So let's go back to the spot. So okay, let's actually make it easier. So 1.5 is actually in the boundary, so I'll make it something in between. So let's say I have a time period of t, capital T equal to 2. I divide it into 4 intervals. What are my 4 intervals? 0 to half, half to 1, 1 to 1.5, and 1.5 to 2, right? Now let's say my small t value is 1.2, okay? So it's obvious that it's going to lie in the interval 1 and 1.5, right? If that is the case, the 2 intervals that I've crossed before I reach small t equal to 1.2 are the intervals 0 to half, half to 1, right? Now, the fraction of time that I've elapsed is t over this equation over here, t over capital T minus the floor of t over capital T, which means the total amount of time that I've elapsed minus the intervals that I've crossed. That would give me the fraction of time in the interval that I've elapsed, okay? Again, going back to our example, capital T is 2. We have 4 intervals, 0 to half, half to 1, 1 to 1.5, and 1.5 to 2, okay? We suppose that small t at some instant of time, small t is equal to 1.2, okay? What is my t over capital T value? That is 1.2 over 2, right? Minus 1.2 over 2, the floor of that is a 1. So what we end up with is 1.2 over 2 minus 1. Now that would give you, if you may, a negative value, right? Yes or no?
Yeah.
Okay. So that negative value, I mean, if you disregard the sign, the magnitude is the amount of time that you have elapsed. So basically what you have done is you're in the range of now 1 to 1.5, and you're in the range of 1.2. So basically the fraction of time that has elapsed, if you intuitively think of it, is 0.2, right? Yes or no? Does that make sense? Okay, let's go over the example again. So we have small t is 1.2, capital T is 2. The floor of small t over capital T is 1 because it's 1.2 over 2. Okay, so what do we end up with? So 1.2 over 2 would give you 0.6, right? Yes or no?
Yeah.
It's 0.6 minus floor of 0.6, that would be a 0, right?
Yeah.
So your interval t over capital T minus floor of t over t is 0.6. That is the time elapsed in the fraction 1.5, but in 1.5, okay? That is exactly how far the interval 1.2 lies in the range of 1 and 1.5 from 1, obviously. Is that making sense?
Yes.
I'm sorry, from 1.5. I'm sorry. So again, so in the range 1 and 1.5, the point 1.2 is 40 points away from 1 and 60 points away from 1.5. That is what it's telling you, okay?
Got it.
Okay, cool. All right. And it's obvious that this number is always going to lie between 0 and 1 because it's a fraction where capital T is always greater than small t. So it's always going to lie between 0 and 1. Okay? And this is the mathematical part that I was telling you about. So from geometry, a line segment with connecting 2 points, x1, y1 with x2, y2. It has a value at x. If you have a line segment at x1, y1 and x2, y2, and if you wish to find the y value at some point between x1 and x2, let's call that point x. That is given by y is equal to y1. That is your y-intercept over your slope. This is your slope. That is x minus x1 over x2 minus x1 times the intercept. Okay. Yes. Looks familiar.
Yes.
Okay. And this is exactly what we're doing. This is your slope value. This is your intercept, and this is your sort of base intercept, if you may. This is your starting value. Okay. And that's exactly how you generate a solid waveform. Here's an example. So let's say we have the time period t equal to 2, minimum value of signal 3, maximum value of signal 6. The generalized equation now, after replacing S min, is now 3 t over 2 minus t over 2, the floor of t over 2, and this would be 6 minus 3, that's a 3. And basically what we are doing is we're taking different instances of time. T equal to 0, the floor is 0. So your S value is S min, that is obvious. At t equal to 1, we have 3 plus 1 over 2, that's a half. Half minus half is is, I mean, half minus the floor of half is going to be half because the floor of half is 0 again. Times 3, that's going to give you 9.5, and so on and so forth. So basically, this is how you generate a waveform. Any questions before I move on?
No.
Okay, cool. Okay, now here's the deal, right? For this lab, we have to write all of this in Python and return a sawtooth signal, okay? So we have to define this function called def sawtooth. What does it take as input? The time instant t, the capital, the time period value, the S min and the S max. Okay, the deal is this t now is a vector, okay? So we have to pass this small t value as a vector into the sawtooth, okay? We can pass this as a scalar. Is that making sense? So this is a scalar value, this is a scalar value, this is a scalar value, but this is a vector now, okay? And so we can call a for loop for t in or t in t set or something like that and pass in a single scalar value to the function and get that, okay? You can't do that. You have to pass this value as a vector and get a vector of values back, okay? That is the idea. Make sense?
Yeah.
Cool. All right, Fourier series approximation of the sawtooth signal. I would believe that most of you are not familiar with Fourier series. Has anyone taken any signals and systems class at any point?
Yep.
So you guys are familiar with Fourier series?
I am.
Teacher went over a little bit.
Yeah.
Okay, so
Not
I mean,
really.
to be very honest, this lab or this course is not about Fourier series, so I'm not going to focus much on Fourier series. But the idea is I'm going to introduce you to the equation that is a Fourier representation of any signal. So since we are specifically talking about a sawtooth waveform over here, the Fourier representation of a sawtooth function is given by this equation: half of S min plus S max minus 1 over pi S max minus S min, and then you have the summation. The only thing that you need to note over here is that the limit of the sum goes up to infinity. Now, since we live in a real world, we don't have a supercomputer at our disposal, so we have to truncate that value from infinity to some value that is computable, right? So a k approximation of a Fourier series takes in the same equation. The only difference is now we truncate the value to k max. So we said, okay, so how many terms do we want to approximate the Fourier series? You supply that value into this equation and you get your k level approximation of a Fourier series. Okay, and it's obvious that if you increase k max, your approximation is going to be better and better. Okay, so this, I mean, to be very honest, there's no point in describing what this equation is doing, for at least for the sake of this class. For now, just assume that you're given this sort of complicated equation, and all you have to do is code it up. That's all you have to do right now. Okay, right. And here's an example of how at time period t equal to 1, S min is a -1, S max is a +1. So this is your Fourier series representation with these values, and you basically find out S1, your k. So your S1, 2, 3 are all k values that you're supplying, okay? So as you increase your k values, your approximation, these equations are gonna get bigger and bigger, which means you're gonna get an approximation much better every time. John, which part did you not get? Fourier series or sawtooth? Which one?
I think that was a answer from before. If you understood Fourier series.
Oh, okay, my bad. Okay, so this is a plot of a Fourier series approximation of sawtooth waveform. So over at the top you have the original waveform sawtooth. What we are doing is we start out with the very bad approximation of the sawtooth, and if you keep going up, so this is approximation with k equal to 1. If you see, this almost gives you a sort of like a sinusoidal curve, right? But if you keep on increasing the k value, it gets closer and closer to something that would look like a sawtooth waveform. And take a look at this. This is for k equal to 10, I believe. Yes, 10 term approximation. Now this looks pretty close to a sawtooth waveform, okay? So that is what you have to do for this lab. Generate a plot that would look like this, depending on what value of k you take. And what else do we have? Oh, so this is how you define the sawtooth approximation. So write a Python function to return approximation sawtooth. So basically, you pass in again t as a vector, k max is a scalar value, everything else is a scalar, except for the small t value, which is now a vector of time intervals that you're going to pass in, and get a vector of Fourier approximation value and plot that. Okay. Right. Anything else that I need to talk about before we start the lab? Yeah, that was the last one. Now, what I would suggest is you download the notebook file that is under week 4, and start with the sawtooth function. I'm going to stop sharing my screen. Start with the sawtooth function, and I would like all of you to turn on your screen sharing, or most of you, whoever can, and show me what you're doing so that I can tell you where you're going wrong with if you're going wrong with the code. So I would like to see some of you, if not the sawtooth approximation, but try to do the basic sawtooth, okay? Sounds fair?
Yep.
Okay.
Yeah. So is anything turned in today?
No, nothing. Just everything is for the lab, and once the lab is over, you're done with it.
Okay.
So do turn on your screen sharing so that I can see what you guys are working on.
So I'm kind of interested. Do you do any research right now? Or were you doing any research before this? While you're also
so I
TA?
work with Dr. Weber as a PhD student. So I work in mathematical modeling and optimization for wireless networks. That's
Okay.
research is.
Nice. Like so in wireless networks, I mean that's pretty broad. What's your
So
focus?
basically, my project is on this network paradigm called LoRaWAN. It's a long range wide area network.
Mhm.
So what we do is we're trying to find out methods for math. So what I do specifically is build mathematical models that would sort of, for example, give you a throughput, better throughput than what you currently have in the market, maybe, and then bound the throughput. So basically, let's take an example. You have these frequency bands out there, and you have
Mhm.
there's multiple like huge number of radios or wireless devices that you want to allocate to this frequency bands. How would you allocate them in a sort of in an effective way so that you
Yeah.
can maximize the network throughput, right? And you devise these algorithms and find approximation bounds, and it's a little bit of game theory involved with you try to find this Nash equilibrium and stuff like that. So yeah.
Mhm. This is dynamic though, right? So it's switching for like, is it for home networks or what kind of networks are you looking more
So it's
into?
basically for IoT networks. So it's all
Okay.
large scale networks out there. Yeah. I mean, if you have
Nice.
a small network, you don't really need an optimization. So
Yeah, that's what yeah. Okay. So it's a pretty dynamic system then, trying to allocate bandwidths for your
right, yeah,
Wi-Fi.
it's all dynamic. Yeah.
Cool. What do you code in usually for that?
So Dr. Weber prefers this thing called Mathematica.
Mm-hmm.
So I try to use Mathematica and it's good, but it has its limitations. So I also do stuff on Python. So yeah, it depends on what I'm trying to code. So yeah, if it's like something that the library is not available in Mathematica, I switch to Python. If it's something easier to do, I just do it in Mathematica. Yeah.
So Mathematica is its own language. Does it have any similarities to any other languages or?
So it's kind of similar to MATLAB, but I wouldn't say that because Mathematica is more like an environment where you you have everything inbuilt. So for example, if you have to do an optimization in Python, you have to the minimum number of lines of code you have to write is almost 50, right? And for Mathematica, just one line of code. You just call
Wow.
If you ever use Wolfram Alpha, it's very similar to Mathematica.
What's
Oh,
that?
interesting. Okay.
Wolfram Alpha.
Oh yeah, I do use that, but that's an online resource, right? You don't have a like.
It's an online resource, but it's offered by Mathematica,
Right.
and
Okay. Yeah, I've used it a couple of times. Yeah.
and the syntax is well, Mathematica is much more broad, obviously, and much more
Right.
capable, but the syntax is very close.
Right. Yeah.
I also had one more question. Sorry, everybody, if we asked a bunch of questions, but for Jupyter Notebook, so you seem very into Jupyter Notebook compared to the other TAs. What do you see that's in Jupyter Notebook versus using like a IDE like Anaconda?
So here's the thing, right? So back when I used to use MATLAB for my coding purposes, I used LiveScript, right?
Yeah.
Sorry, and I found that very intuitive. That I mean, you can see the plots and you can like interleave text and stuff and do cool things with LiveScript. I mean, it has its limitations. I find Jupyter Notebook way better than LiveScript since I started using it. So the thing with Jupyter Notebook, at least in my case, I find it very intuitive. I can, so if let's say I have a presentation to make, I can just like put in my figures and my plots and equations and everything, and it makes it look good. So that I mean, I don't have like an affinity towards Jupyter Notebook, but it makes my work easier. That's all.
For a TA job or something like that.
Yeah, for a TA job, or for example, I've presented in some research meetings using Jupyter Notebook, and it went pretty well.
Okay. Cool. Thank you.
Yeah. Do you guys mind if I turn off my video?
No, go ahead.
Cool thing.
Hey, I have a question. Can you
Sure.
look at something?
Sure, yeah.
All right, so I'm gonna go share screen.
Mm-hmm.
All right, so I plug in the variables t smin and smax, but like it doesn't go up to 2 all the way. I do 1.
Okay, let me take a look. Smin plus t over t minus np floor, right? So S max minus Smin. Okay, so we're taking in but your S max is 1, right? If I can see correctly.
Yeah.
So it's going up. Okay, it's going up all the way to 0.6. Okay. So let's take with that t equal to half. Interesting. T min is 0, T max is 7, and you have 70 points in between, I believe. And 12.6. Oh, can you? So let's do one thing. Let's change -1 to 0 and see what we're getting. Make the 0. On that for me. Instantaneous values. All right. So I'm starting with 0. Let's just hold on. Starting at 0. So my at t capital T equal to half, my small t value would be what? So I have half of. So if my t value is 1, S max minus S min, that's a 1. So basically what I'm at end up with is basically t over t minus the floor of t over t, right? So for this given value. And initially I had, okay, S max minus S min. So that is 2t, 2 times small t minus floor of 2 times small t, right?
Right.
So my t value would be, if my small t is 7, then I have a 14 minus 14, that's a 0. Anything in between. If I have a fraction, 2 times a fraction. Can you just print out your t small t array? I just want to see the values. Right. So let's say, what do we have when we have a 0.3, for example? So 0.6 minus 0.6, 0.6 minus 4 of 0.6, that's 0. 0.7 times 2 times 0.7 is 1.4. 1.4 minus, yes. No, it's not going to go up to, it's not going, I think. So what happens when we have 0.5? So that's 1 minus 0. Huh, that's weird. So at 0.5, t equal to 0.5, we should have 1 minus, oh, no. 1 minus floor of 1. That's a 0. Right. Yes. So at 0.4, yes. So if you go down, look at 0.4, okay? Look at this value, 0.4. So 2 times 0.4 is 0.8. Minus floor of 0.8, that's a 0. So the largest value you would get is a 0.8. Because if you multiply 2 times 0.5, that's a 1. And 1 minus floor of 1 is again 0. So you come back to 0. So it's not necessarily that your signal might go up to the S max value. But that's fine. I mean, it's all about generating the sawtooth. It doesn't necessarily have to go all the way to S max.
Yeah.
It depends on what you're taking as an input, but yeah.
Yeah. This is weird.
The Fourier series or this?
No, this. That it
oh.
doesn't go up to 1. Or does it? And
No, it doesn't. Okay, let's take a moment. So what are your values? So you have -1 and 1, and your capital T is 1. So your S max minus S min is now a 2, right? And
right.
your S min is a -1. So 2 times T over, and what's your T value? That's a 1. So 2 times T minus 4 of T minus 1. That's what you're having, right? So
Right.
let's take 0.5, all right? 0.5 is T. So that's 2 times 0.5, 1 minus 1, that's a 0. Again, at 0.4, you have 0.4 minus floor of 0.4, that's 0.4 times 2, that's a 0.8 minus 1, that's a negative value. So at 0.5, you have a 0. So you would get your maximum at 0.3, I would believe. So that is 2 times 0.3 is 0.6 minus 1, no, still a negative value. Where is it maximizing? 0.6, that's what I don't understand about the plot function is the parameters. For instance, plot dot pltt creates plot if it is an iterable numerical array such as Python, but S could be just as a designated name for. Okay, let me take a look. Plot t comma S. For instance, creates a plot if T is an iterable. No, here's the thing. To answer your question, John, if you run the sawtooth function with the values, small s is a vector. It's an array. It's not a numerical integer value, or it's not a single value. That's the idea of a vector, right? You pass in a vector and you get a vector.
So you're passing in a vector into this.
You're passing in a vector into the sawtooth function, and what you're getting as an output is also a vector.
Yeah, so you're passing in T and T, lower,
right?
Small t and big T. Small t doesn't get modified, but big T does.
Why would that be?
Because you want it to be like modifying.
So I'm sorry I didn't get you. So you're saying capital T gets modified?
Wait a minute. Oh, I think I know why. Basically, it goes from 0. All right, so right now it's going from 0.2, 0.4, 0.6, 0.8, and then it goes to -1. It should go to 1 and -1, but like it just going to -1 because like that's just how it works. That's just how the cookie crumbles. Like, I get it now. It's because look at that.
This is these are your t values, right?
Yeah, if you had a lot more points in between,
Make it 100, will you? Make it 100 or 101, something like that.
yeah, exactly. Look,
Yeah,
that's why.
yeah, it's a interval, yes.
Whee! It's
Yeah,
gonna take a long time to graph. Oh,
you can delete
there we go. That's it.
Yeah.
Yeah, that's why, because you didn't have enough points. That's the only
exactly,
reason.
yes.
So,
Does that answer your question, John? Or so S and T both should be arrays, yeah. By passing a vector to function as a parameter called the function one. The resulting value. Exactly, yes, exactly. That's what is happening. Right. Okay.
Okay, can you hear me?
Yeah.
All right, so I have kind of a dumb question right here. So when we're implementing the instance of the Fourier approximation of the sawtooth here, we're not actually using this part. We're going to be using this part right here.
No. We are using everything. So what we're doing is in this function sk, we're just writing this part of the equation inside the summation. That's all. Inside the summation.
Oh, so this part right here.
Yes, exactly.
Yeah, okay.
That's what goes into sk, and then you call sk into the sawtooth approximation where you include the other terms as well.
Okay. All right. So then this would be in a for loop, too.
Which one?
For this summation here, it would also be in a for loop as you're cycling through, since is the vector, correct? This is the vector right here, t.
Right, but yeah. But here's the thing, right? sk should yes. I mean, not a for loop, but you have to pass it as a vector. Yes.
Oh yeah, because it's going to be calling it in a for loop.
Exactly.
Okay.
Yes. Yeah.
Oh, okay. Sorry. All right. Thank you.
Yep.
So what is the differences between the approximation and the actual Fourier series representation that we just did in those two lines?
So the deal is are you talking about the actual Fourier with the limit tending to infinity, or?
Yeah. So just going back to what I just showed you right here, they're pretty much the exact same.
Right. So what is happening is that a Fourier representation. So here's the deal, right? In a real world, when you're transmitting a signal, and let's say you're in a wireless setting, you have to sort of encode your signal to send it out, right, over the physical channel, right?
Yeah.
And it's obvious that you can't send out a binary or a sort of signal in just the way it is. You have to encode it and sort of modify it, sort of modulation scheme, if you may, before you send it out. What approximation does, what Fourier series does it, it does that modulation part of your job, right?
Mhm.
So it sort of makes that signal sort of more robust when you're sending it out. But here's the deal, right? To make that signal as close to possible to the real signal, you have to have the approximation as large as possible. You have to go down to that, let's say, 1,000 decimal place of approximation to mimic the original signal. But that is not possible in real life, right? Like going down 1,000 decimal place would take a huge amount of computation power. So what
Yeah.
we do is we sort of truncate that or relax that constraint that, okay, we don't have to approximate so much. Let's cap it at, let's say, 100, k equals 100. So we are happy with 100 places of decimal, and that in reality would give you a fair performance of how it would be in the real signal as well. So yeah, that's the deal.
Okay. And then so we're just going to be putting this. So the first one we just put the summation to the infinity.
You
And
put
then
the
for-
summation. You put the part inside the summation. So the summation takes place inside the sort of the props, where you sort of use a for loop, like a vectorized for loop, to get the value of the summation. Yeah.
Yeah, but for the first one, we only had to do this summation
Right,
part. For the
exactly,
second one, we have to do the entire equation.
Exactly. Yeah.
Okay, thanks.
How do you implement SK into sawtooth approx?
You just basically call a function.
Yeah.
Can you share the screen?
But there's no K inside of that's called within sawtooth approx.
What do you? Can you share your screen? I just want.
Like, do I have to pass in K max into SK?
No. So I mean, basically, what you do is so what are the, let me take a look. What are the inputs to the SK? So it's T, K, and capital T, right? So yes, yeah. So when you call the function SK inside sawtooth approx, in place of K, what you pass in is K max as an input, right? That's what you do. But here's the deal, right? You have to find out the summation value inside the sawtooth approximation. So you have to find the summation value there.
Okay, so I just shared my screen.
Who's that? Is that a soft? Or,
Yeah.
Yeah.
I'm getting some errors. I was hoping you could.
It's on the first one or the Fourier? Which one is this?
The Fourier.
Fourier, okay. So let me take a look at SK out is equal to -1 to the power of K times 1 over K times NP dot sinusoid. I hope the parentheses is fine. Let me, what was the real equation? So it's 2 times NP dot pi over
K
T
times
times
K.
K, right, times T minus, right. Okay, fair enough. Now what is happening over here? A is equal to,
Right, because that doesn't change.
to be honest with you, oh, it's out of vector, I'm sorry, yes. A is equal to half times S min plus S max minus n 1 over pi times S max minus S min. Out is, so you don't need to do that. You don't need to write this out equal to, you don't declare that. You can just write out is equal to, what do we have?
I thought I need to loop over the values of K for
Right,
all.
but you can do that in a single line, right? You can write out is equal to A plus summation of whatever that is for K and for I in range, that kind of thing. You know, the vectorized for loop thing.
Okay.
The loop comprehension is what they call it, I think. Or list comprehension, I'm sorry.
Okay, so what would that look like? So for
So A plus, or what do you have? You have multiplied. So no, you can't actually take A because you have half. So just make A equal to half of S min plus S max. Okay, just make that. Get rid of the other part.
wait, A equals half.
Yeah, just so that
Get
part
rid of
is
this?
multiplied. That part is multiplied with. So you can put that as B. You can put this whole thing as B.
Oh, I see what
Yeah.
you're saying. I see what you're saying. That makes yeah. That part is not multiplied. Yep. That's definitely a mistake. Okay.
Right. Now you can write A minus. No, you can remove. You can get rid of the minus part from B. Yeah.
Oh yeah, I could just
Yeah.
build it in. Okay.
A minus B times. A minus B times. What do we have? SK or within square braces. You can write. What do we have? Some. Or you can you know what you can write. Hold on. So A minus B times sum, and the command sum, and within parentheses, you have get rid of the square braces. Get rid of the square braces.
Oh.
Sum. Inside you have now inside the square braces. I'm sorry. Inside the parentheses, write square braces.
Ah, okay.
Yeah. Now call SK with the input SK. What do we have? TK capital T. Capital T. For
But K is not passed in as a parameter.
Yeah, that's what we're gonna do now. So now get out to the parentheses.
I see. I see. Okay.
For K in range, whatever you had.
For K in range
1 to K max plus
0
1.
to K max.
No, I think it was 1 to K max plus 1 previously, right?
Yeah, that's what I had previously, but
Because we're not starting from 0, we're starting from 1. So over here you have K equal to 1 to
oh,
K.
they're right. That would be like a DC component.
Right. Yeah.
So 1 to K max plus 1.
Right. Now that should work. Hopefully.
Okay. Let me run this
See.
again. Oh.
What is the error we're getting this time? For this thing? Go.
X and Y in format string must be none.
X and Y format string. Interesting. Which line is it? Oh, hold on. Plot of it's giving me an error at plot. Okay. So what is it? What is A again?
A, they said, is sought through the procs.
Okay, so once we have that plot function.
Oh, wait 1 second. I'm not returning anything.
Oh yeah, my bad. Yeah.
Returned out.
Right.
There
right.
we go.
Yeah.
Cool.
Right. So for the homework, you have to do something very similar. Only it's just 3D and not 2D. That's all.
Okay.
Yeah.
I still need to wrap my head around the list comprehension stuff. I've been doing
Yeah,
MATLAB.
it's a little tricky, but once you get used to it, it's gonna be all fine. Trust me.
Yeah, it's a shame MATLAB doesn't support anything like that.
Does it not? Oh, okay.
Not in such a robust and
Right. Oh,
and
yeah. That's
straightforward manner.
Yeah.
Cool. Awesome.
All right. Yeah.
Okay, great. Thank you. Have a good weekend.
You too. Yeah.
Bye-bye.
Okay.
Sorry, could you take a look at my code?
Sure. Yeah. Go.
Yeah, let me share my screen. Give me 1 sec.
Mhm.
Do you see it now?
Yep.
Okay, so I kind of ran into the same problem. I wrote the code for the sawtooth approximation on the same line. For some reason, it's not returning a plot.
Okay. Can you go up? Right. So let me take a look at SK. So -1 over K times 1 over K. Yeah, this all looks good to me. Yes, that's fine. Okay. So what you should do is return. So hold on. Return. Okay. So the only thing that get rid of the square braces and return. Okay.
Oh, sorry.
Get rid of the square braces for return. Yeah, you don't need those.
Okay.
Right, but do one thing. Hold on. Go up. So this whole thing, SK thing. Put a some command over there.
What command?
In the south of the procs. In the south of the procs.
So what command do you want me to?
That's fine. That's fine.
Okay.
So just go down. Go to the sort of the procs function. Right. So this part over here, where you have this SK, TK, capital T for K in range, this thing.
Yeah.
So go to the sort of the procs part and write a sum command around SK. just around the sk and the for loop part. Right, sum and open a parenthesis. Open a parenthesis around this whole thing. And put this whole thing inside of square braces. Just put a square braces on either side. No. Inside the parentheses.
Inside a parenthesis?
Yeah.
Oh, like this.
Yeah, exactly. Let's see if that works. It should. Yeah.
Okay, there it goes. So why do I need to get a sum for the
So
sk function?
basically, so if you go up to the original equation, so we're basically summing it up, right? So what you were doing initially was you're just looping through the values, but you were not summing them up.
Okay. But wouldn't, even without the sum, it should plot anyway, because this would return values and then.
So here's the deal, right? Without a sum, you were not doing anything with the sk. So it was taking just one value of k, iterating, and what we were running into was a dimension error. What you needed was a scalar value. What you were getting was like a vector or a matrix, something like that. So, but what you need to return is a scalar value. It was hoping it would get a scalar value, but it got like a vector.
Okay. Gotcha. So which part would be where it start realizing that it's actually taking in a vector function, not a scalar, not a scalar.
This one, a is equal to sawtooth approx t k max. So when you call this function and you pass in a vector to it, and when it takes a look at, okay, so I have to return this function half of s min plus s max minus 1 over pi s max minus s min, and then I have this sort of vectorized part where this is what you call a list comprehension. Okay, the sum of this whole thing for the square braces for loop. This is list comprehension. So whenever it encounters list comprehension, it understands, okay, so this guy is giving me a vector, so I have to compute a vector now, not a scalar.
Okay.
Yeah.
Okay. So when I start plotting in plt.plot ts, that is when it turned from a scalar value to a vectorized value, right?
No, for the plotting value, it basically plots whatever you're giving it. So you could have implemented this whole thing using a bunch of for loops as well. So the plt.plot function doesn't really care by what method you got the answer, right? But the thing is, if you really want to test what this thing is doing, you can use this command called time it, which sort of gives you the running time of the algorithm. So what you can do if you have spare time is like rewrite this function using a bunch of for loops and see how much time it takes that to run against this one, okay, using the time it command. Yeah, and you would be surprised to see that if you vectorize it, you would get a much lower running time compared to your nested for loop version.
Okay. Gotcha. All right. I think that's the.
Yeah, that looks good to me. Yeah.
Okay. All right. Thank you.
Yep.
Hey.
I have one question. Oh,
Go
sorry,
ahead,
you go. No, I've been asking questions all day. You go, dude.
You're all good. I kind of want to just share my screen and then get a little help, and I think I'm good. So you go ahead, Dave. I'll do it after.
Okay, I should take a couple seconds.
Yeah.
So I'm pretty much there. The approximation. How do I increase? So how do I declare I want more? I'm only getting one approximation right now.
Oh, so you basically make k max equal to 1,000 or something like that, if you may. Let's see what that. Did you run it or?
Yeah, I did. Yep.
Let me take a look at your.
Oh, I actually don't declare K-max in here. I think that's probably the problem.
No.
I do. Just kidding.
Yeah, take it.
See, why is my for loop not colorful like everybody else's?
Oh, that's a good question.
I mean, even my return and my defs aren't even colorful.
What do we have? One space, more -1, -2, -3 to 3. For loop.
When she was going over hers, I just double checked mine to make sure mine looked good. And it looked fine. So I'm just really confused what I did wrong.
No, I don't see anything wrong in here. Just let me check.
Oh, I'm sorry. You want me to stay here? Sorry.
SKTK capital T for K.
Hey, how do you fix int object is not callable?
Well, you kind of like bunch of reasons why you would get that. So just hold on for a moment. I'll come back to you.
Alright.
Huh, that looks pretty strange.
You want me to scroll up or stay here?
No, this is good. I'm just trying to understand what. Hold on for a moment. So in your sawtooth approx, you have a parentheses starting with a parentheses, but I don't think you're ending with a parentheses for the main one.
That could be it. I mean,
Can
want to run that?
Yeah, let's go and see.
Nope. That didn't like that at all.
Error? So what is it? What is it? Then that parentheses for. Hold on, what is happening? Oh.
I think I see it.
Get rid of the parentheses. In the before sum. Get rid of the parentheses before sum and the beginning. Yeah, get rid of that. And one at the beginning. Yeah, that should work. Huh? Hold on.
You forgot to remove that end parentheses that you added.
No, that was for the sum, right?
Oh.
Yeah, that was the sum.
That's for the sum.
So S max 1 over n prime.
Oh shit! I pressed the wrong button. Sorry about that. I was trying to make it bigger for you so you could see it.
No, it's fine. It's fine. So I have half times 0.5, half times S min plus S max.
Sorry, Tom.
Minus 1 over.
Dude, it's all good. I'm learning while watching you guys.
S max minus S min times sum. Less negative K. Sinusoid, like 2 pi.
It has to be that it's not going through the for loops, don't you think?
Because hold on. You go to your SK. You're missing a K over here. Inside over here. So that's 2 pi over T times K times T minus. You don't have the K over there.
I'm sorry. Let's see here. What are you saying? Let's see. 2 pi over T
times K times T.
Yeah. God damn it.
Yeah, there you go.
Oh, thanks.
Yeah.
Oh man, I just dyslexic, I guess. Sorry. All
right,
no,
don't worry about it. It's fine.
Hey, I'm gonna share my screen right now.
Dude, let Tom go, bro. Seriously.
Okay.
Dude, I think we have the same problem, Jordan. At least I'm getting the same error, so maybe we'll figure it out.
All right, you can share your screen then, Tom.
Thanks, man. Can you see the screen?
Sure, yes, I can.
Okay. I'm getting that. I don't know if Jordan's getting the same one, but I'm getting that.
And the object is not callable. Okay, let's take a look at your function first. Return negative 1 to the bar. K sine 2 go to. Oh yes, you have to write K times. It's K times over here in def SK.
What's that?
Def SK. You have K times T minus capital T over 2.
Sorry, I don't know what you're talking about.
Def SK. So the function SK.
SK. Yeah,
go to the last part. You don't have K star. Look at that. K star. It has to be K star. K times T minus.
Oh, K star.
Yeah, that should work. I think that is the problem.
It didn't fix it for me.
I didn't fix it for you either. Let's go back and check what else.
Oh wait, no, it did. I just had to run it a few times. Is this what you're looking for?
Yes, that's what you should get.
All right. Thank you. I'm gonna stop sharing my screen so you can help Jordan.
Sure.
Thank you.
All right. All right.
Yeah.
I don't know. I'm getting it.
Hold on. Okay. First of all, do you mind putting out the power exponent thing outside the parentheses? -1. This whole.
Why?
Yes. No, put a parenthesis around -1. Just put a parenthesis around -1. Okay, and yes.
Wouldn't that be like 1 to the power of k and then to the power of all this?
Put a star. Put a star after k.
All right. Okay. All right.
Right.
Let's see what happens now.
Let's see.
Float object is not callable now.
Okay, let's go up and see. I think these are mostly syntax errors. So -1 to the power k times 1 over k times then. Oh yes, again we have the same problem over here.
Over here?
Yes, but between the parentheses, you need a star between the parentheses.
I did it.
No, before k.
All right. Okay.
Yeah, right there. Yes. Yep. There. Hold on. There's something wrong with your main plot. Can you show me your sawtooth waveform? 0.5 times S min minus 1 is 0.5. A times B minus 7.
I think it's multiplied by pi. Isn't it supposed to be divide?
Oh yeah, that was a dumb mistake. Okay.
Oh yeah, right there.
Okay.
Yeah, there you go. I mean, pretty close, but there's something's wrong. Is it half times? Hold on. What was that equation?
Oh.
It's 1 over pi, not half over pi. Yeah, it's 1 over pi.
Oh yeah. Okay.
There you go. Yeah.
Now, how did that person add a sine wave?
Which one?
How did that other person add a sine wave?
Oh no, that was a mistake. We fixed it, right?
Pretty cool mistake though.
Yeah, I know. I mean, that is the thing with Fourier series, right? You tweak a little bit and you get something entirely different.
Yeah.
And it still looks cool.
Yeah. See what happens.
Oh, that won't work. Oh, you turn to plus. Yeah. Yeah, you won't get it. Your sign flips.
That did not do anything, but all right.
Well, it did do something, but
all right.
The deal
there
is,
we go.
Yes, the deal is when you put the negative sign before that, that's your constant phase, right? So whatever is changing in this negative b times this part.
All right. Okay, I'm done with the lab. I did it.
Okay, cool.
We're done.
Okay, somebody, let's see. Let's open. Yes, Dominic, that's the correct one. We are going over this week's lab, Alicia. It's in the week 4. You have to download the notebook and work on it if you haven't worked on it yet.
Can I ask a question?
Sure, yeah, go ahead.
I'm gonna share my screen real quick. Can you see my screen right now?
Yes, I do.
Okay, so this is where I'm at.
Okay.
I just retyped the formula. I might have done it wrong again. I don't know.
Let's see. Same issue. Okay, let's take a look for. I see. So okay, hold on. In SK, you don't have to use a for loop. You just define the function. That's all. You don't have to use a for loop. Any for loop stuff would happen inside sawtooth.procs.
So I can just get rid of that.
Yes, and try running this again. Okay. Let's see what we get. Okay. There you go.
All right, cool. Thank you.
Yeah, sure. John, do you mind sharing your screen so that I can see what's going on?
Can you hear me?
Sorry, was that?
Can you hear me?
Yeah, your voice is a little low though.
Yeah, my microphone's not that high quality.
Oh, okay, that's fine. Let's see. Okay, let's go up and take a look at the functions. -1 to the power. Okay, hold on. -1 to the power k divided by k. Can you make it star 1? Yeah. Put a star and then 1. Yes. Times n theta sine the 2 pi and hold on. 2 times pi over t times k. Okay, that looks fine to me.
Next, then this one.
Yeah, I'm just taking a look at that. Half times S min. Yeah, that looks fine to me. Let's go and run this and see what we get.
Wait, run it again.
Yeah, run it again.
Now I run this.
Mm-hmm. Same problem. Let's go up and see.
I can't hear you that well.
Oh, you can hear. Can you hear me now?
I can, yeah.
Okay, can you go up? Go to the function part. Yeah, hold on. Okay, so what do we have? We have 2 times np pi times plus half times s min plus s max minus 1 over np dot pi.
Oh, wait a minute. I think I figured out the problem.
Oh, you had a parenthesis. Oh, okay. Yeah.
Let's try running that again.
Yeah. Go ahead.
That's because it kept saying us adding a list to an integer, and I realized why that would be happening.
Yeah. Yeah. There you go.
Oh, well, I guess I figured it out myself.
Yeah.
Yeah, there. You saw it, right?
Yeah. I mean, these are. I mean, these things happen when you write code, like syntax problems and everything. So.
All right.
Yeah, that's all good. Any more questions?
Hi.
Yeah.
I think I got it done, but can you just take a look at?
Sure. Yeah. Sure.
So maybe there's something I can improve.
Sure. Yeah. Go ahead.
So this is the first one.
That's a sawtooth waveform. Okay. Hold on. S is equal to S.
I realized that if I take up the loop here, it still return the same thing.
I don't think you need a loop. You don't need a loop for the sawtooth function, to be very honest. You can just put the function over there and return that. You don't need that.
Like this.
Yeah, I mean, yeah, that should work. Yeah, you don't need the loop. I don't see a reason why you should need loop. But S min, S max minus S min, okay. Turn S. Interesting. And why do we have? Oh, it's up to 7. That's why. Okay. Can you make it an 8 or something? Yeah, like yeah. There you go. Yeah, it looks fine to me.
Thanks. And the second problem I see the screen sharing. So
Sure.
I mimic that.
Yeah. This. Can you go down and can I see your plot? Yeah. This is fine. This is fine. Right. So the more you increase the Kmax value, this is gonna get better and better. Yes.
Yes. All right. So I think I got it.
Yeah.
I'm good to go. Thank you so much.
Sure, no problem. Take care.
All right, I'm going.
Having some issues with mine then.
Sure.
Too.
Yeah. Go ahead.
I feel like it's probably not that complicated.
Sure. Let's see.
Yeah, so it's saying that sign is not defined.
I think you didn't
here.
use np.sign.
I'm using it here. I don't know where else it would be.
Hold on, let me take a look. -1. Can you go back to your function? Let me take a look at that.
Oh, yeah.
-1 is a barcade. Interesting. 2 times np dot pi np dot sine.
Then like down here.
Hold on. In this sawtooth approx, your SK, this square braces should be around the for loop, not just around SK.
Oh, okay. So like
I'm not sure if that's the error, but let's see if that changes anything.
Like all the way out here.
All the way inside this parentheses for sum, wherever that ends. Yeah, inside the second parentheses. Inside that. Yeah, right there.
Here?
Before that.
Oh, okay.
Yeah, right there. Yeah. Right. Let's go and see what's going on here. Same
thing.
Where
yeah, and like down here it doesn't have MP. So I don't know if that's part of the problem.
Okay, good. Let's go all the way up.
Okay.
Can you run the first function?
Yeah.
Run that. Run this again. Run the final script.
There we go.
Yeah. It didn't take the value for some reason. Yeah.
Great.
Yeah.
All right. Cool.
Yeah.
Thank you.
Yep.
Have a good one.
You too. Right. Any more questions? How is everyone else doing? Are you guys all good? You have a question, Tam?
Not for this lab, but for the homework of week 2.
Oh, yeah, go on.
So, is it possible that we go into the breakout room?
Go where?
To the breakout room in Zoom. I think they have that feature.
Okay. Breakout rooms, I got that. Yeah. Create breakout rooms. Okay. Sign. Right. So can everybody else hear me? Can you hear me, Tam?
Yeah, I can.
Okay. Yeah, go on.
Yeah, sure. Let me share my screen.
Yeah.
Okay. So that is where so I'm still having some hard time wrapping around the assignment. So basically it's so I understand that for this function it's trying to find the probability for each arm. And this one create a MAP, play the MAP, and play the MAP n times and average results.
Okay.
So for the homework, we have to put in the number of arms, the number of trials, and so I'm still a little bit confused about the difference between n, the number of trials, and the number of pools, and the max explore pools.
Okay. So the small n or small n values is the total number of pulls, okay? The total number of time you can play a round of the game, okay? Capital N is the number of rounds of the game that you want to play, okay?
So, so let's say I have 50 pools total.
So yes, that's your small n.
And yeah, n equal 50 for all the machine. And so how does the big N play into this number?
So for n equal to 1, for capital N equal to 1, you have 50 pools on all the machines, okay? For n equals to 2 again, you have 50 pools again on all of these machines. So basically, capital N is a round of the game. So by a round of the game, I mean 50 pulls on each machine. So now you keep on playing this game over and over again. So for capital N equals 1,000, you play this game 1,000 times, okay? Each time of the game, you have 50 pulls. And with all the results that you get over all these 1,000 times you play the game, you average that. Does that make sense?
Yeah, okay.
Okay, and the explore pulls is the number of times, or the number of pulls that you can have on each machine without betting money to find out which machine is the best.
Okay.
Does that answer your question?
Yeah, that answered my question.
Great, awesome.
All right, thank you.
Have a good one.
All right. Have a good one. Have a good weekend.
Thank you.